अस्सलाम वालेकुम एवरीवन। आज हम चैप्टर नंबर 2 को कंक्लूड करेंगे एंड दिस इज़ गोइंग टू बी आवर थर्ड ऑनलाइन लेक्चर एंड द ओवरऑल 18th लेक्चर। सो लेट्स क्विकली start with the presentation. Okay, so a quick recap of the outline. हम लोग अभी तक ये सारे टॉपिक्स कवर कर चुके हैं अप टिल पोलराइजेशन। तो जो लास्ट टाइम हमारी डिस्कशन हुई थी दैट वाज कंक्लूडेड एट दिस टॉपिक पोलराइजेशन, और उसके अंदर हमने टाइप्स ऑफ पोलराइजेशन और उसकी मैथमेटिकल एक्सप्रेशन भी ड्राइव की थी एंड एट द एंड वी एक्चुअली कंक्लूड द डिस्कशन विद एन एग्जांपल एज वेल। सो आज जो हम बात करेंगे विल टॉक अबाउट इनपुट इम्पिडेंस and Friis transmission equation and radar range equation, and that will conclude our chapter number 2. सो इनपुट इम्पिडेंस बेसिकली हम लोग इस पे पहले भी काफ़ी डिटेल में बात कर चुके हैं इन आवर ट्रांसमिशन लाइन डिस्कशन, जहाँ पे हमने इनपुट इम्पिडेंस की एक्सप्रेशन निकाली थी एंड वी एक्चुअली डिस्कस्ड हाउ दिस इनपुट इम्पिडेंस इज वेरी इंपॉर्टेंट इन डिटर्मिनिंग the total power transfer from the generator to the antenna. So आज हम इनपुट इम्पिडेंस के टॉपिक को कवर करेंगे एज ए पैरामीटर ऑफ एन एंटेना. सो लेट्स क्विकली गो टू इनपुट इम्पिडेंस टॉपिक. सो या लास्ट टाइम हमने एग्जांपल 2.11 देखी थी अबाउट द पोलराइजेशन लॉस फैक्टर. सो आज हम बात करेंगे इनपुट इम्पिडेंस की. सो हम लोग अभी तक जो बात कर चुके हैं वी एक्चुअली टॉक्ड अबाउट इनपुट इम्पिडेंस. सो हमारे पास दो केसेस हैं. फर्स्ट ऑफ ऑल द फर्स्ट केस इज द ट्रांसमिटिंग केस एज वी कैन सी ओवर हेयर. सो ट्रांसमिटिंग केस में क्या होता है कि वी हैव अ जनरेटर and the generator is actually transferring power to the antenna through some transmission line. So अभी हम फिलहाल ये assume कर रहे हैं कि जो जनरेटर है वो डायरेक्टली आपके एंटेना के साथ कनेक्टेड है. सो फ्रॉम दिस पॉइंट यहाँ से अगर हम एंटेना की इनपुट इम्पिडेंस को देखें तो इट वुड कंप्राइजेज ऑफ ZA. This ZA is nothing else but the input impedance of the antenna, and it consists of a resistive part and a reactive part, I should say. So and we can see both resistive and reactive part both are the function of frequency omega. अब इसके अंदर जो RA है, RA is the antenna resistance and it consists of two parts. First is the radiation resistance and the other is the loss resistance. और हमने लास्ट टाइम ये बात भी डिस्कस की थी कि जो रेजिस्टिव पार्ट होता है इसमें जो रेडिएटिव part है, this RR is the radiative or the radiation resistance. In this case it is the resistance which actually convert the power delivered to the antenna into radiation, whereas R loss is the loss resistance which is the ohmic and dielectric loss that we actually discussed earlier as well. So ये वो resistance है that actually shows कि how much power is dissipated in the form of heat within the antenna. So अगर आपके antenna जो है उसमें losses नहीं होंगे, so all the resistive you can say part will be the radiation resistance, and the R loss, as we have discussed earlier, it consists of ohmic loss and the dielectric loss. It's the conductive and dielectric losses. सो अगर इसी मॉडल को, ये जो हमने जनरेटर की एक एग्जांपल लिए कि जनरेटर एक एंटेना के साथ कनेक्टेड है एंड हियर वी कैन सी इट इज अ हॉर्न एंटेना, इसको हम एक थेवेनिन इक्विवेलेंट मॉडल से रिप्रेजेंट कर सकते हैं वेयर द जनरेटर कैन बी मॉडल्ड एज ए सोर्स VG एंड ZG इज द इम्पिडेंस ऑफ द जनरेटर, जिसको हम ZG से रिप्रेजेंट कर रहे हैं. एंड जस्ट लाइक ZA वी कैन राइट ZG एज the resistive part of the generator and the reactance part of the generator, which is XG. And here we can see ZG is RG plus JXG. So अगर हम इसी मॉडल को देखें तो we can see कि the current that is flowing through this Thevenin equivalent circuit is IG, and this IG can be determined using, if you remember, we can use the V is equal to IR, which is the Ohm law. In this case I is V over R. So if we apply this Ohm's law into this particular circuit, we can see V is nothing else but VG, and the total R in this case is the generator impedance and the antenna impedance. So this is IG in this case. So we can say that the current flowing through this circuit is VG over ZG plus ZA. So and in this case VG and IG are the peak values. So the condition for maximum power delivered to the antenna is that you have a conjugate match. And what is a condition for conjugate match is that your RA should match with RG and XA should be matched with negative time XG. This is because we want to cancel out the reactance part, because if you remember हमने जो ट्रांसमिशन लाइन की डिस्कशन की थी, we said कि आपके पास ये जो reactance का part होता है that actually cause those reflections, and because of that you get those standing wave ratios. So for maximum power transfer, our RG should match with RA, and the reactance part should be conjugate of each other, so they would cancel each other out. So if we consider this particular case, we can actually determine the relationships for the current IG and the power loss PL, and the generator power, how much power the generator is actually generating. We can calculate all these values. So first of all, when we're talking about conjugate match case, in this particular case, as we said, IG is VG upon ZG plus ZA. So this is same as VG over ZG is what? It is RG plus JXG, and ZA is RA plus JXA. And if you apply this condition on this, we can easily see this will become VG over 2RA, because RA is RG, XG and XA will cancel each other, and we will get IG equal to VG over 2RA, which we can see over here as well. So I will not be writing down every equation over here because of the time constraint. What we will do is that we are going to talk about the relationships, and we will discuss it over here. So here you can see this actually leads to the relationship of power radiated, and we know power radiated is equal to 1 over 2 Ig absolute square, and this is the radiation resistance. Why this is 1 over 2, that power is now half times? It's because if you look back at this Thevenin model, we see for conjugate match case, RA and RG both are same. It means this impedance and this impedance both have the same resistive part. So in this case, whatever power is generated by this source, half will be dissipated around this within the generator, and half will be delivered to the antenna. So the total power delivered to the antenna in case of conjugate match case will be half of that generated by the source. So in this case, you will have P radiated 1 over 2 Ig square over R. Then this is the same the formula that we say C for power, which is P is equal to I square R, or power is equal to V square over R. So we're just talking about that power expression. So now if we look at the radiated power, in this case is 1 over 2 times Ig absolute square RR. So we plug in the value of Ig, which we have found out for the conjugate match case here, into Ig. We would see that this comes out to be this particular expression over here, which is Vg absolute square upon 8 radiation resistance over, this is the overall antenna resistance Ra. And I will just try to simplify one expression for you, and you can apply rest of the expressions yourself. So as we know that Ig is Vg upon 2Ra, and we know that P radiated is 1 over 2 times absolute Ig square into radiation resistance RR. So in this case, if you plug in this value over here, P radiated would be 1 over 2 times, this is Vg absolute over square of 2 is 4, and you have 2 times Ra into RR. So in this case, 2 multiplied by 4 will be 8, so it will be Vg absolute square over 8 times Ra square into RR. And we know what Ra is. Ra is RR plus R loss. So this is what we can see over here. This is the expression that we have just derived, and this is for the radiated power. So this is what is radiated power in this case. And if we talk about the P loss, so this is the power loss because of the loss resistance. So again, the expression will be 1 over 2 times Ig absolute square. Now the resistance we are going to consider is the loss resistance, and again, if you plug in Ig over here, you would see that P loss would be like this. So this is the power loss to heat at the antenna. And if you want to find out the power generated by the generator, so it would be Pg is equal to 1 over 2 times Ig absolute square Rg, because we know Rg and Ra are same for conjugate match case. Half of the power will be dissipated within the generator. So this is basically the power loss in Rg. So in this case, just plug in Ig over here, you would see that this Pg is equal to Bg absolute square over 8, 1 over Rr plus R loss. And you can think of it the same way, this as we have Rr plus R loss whole square, and in the numerator you will have Rg, and we know Rg is equal to Ra, and Ra is Rr plus R loss, so that will be cancelled with the square term, so you will have 1 over Rr plus R loss, which is also given over here in this case. So in this case, because we have a conjugate match case, the P radiated plus P loss will be same as the power loss in the generator. So this is the same thing that we discussed earlier, that half of the power is actually lost within the generator and half of the power is delivered to the antenna, and within this power, P radiated is the power that is radiated, and P loss is the power which is dissipated in the form of heat. So this equation will be will satisfy in this case. So if we talk about the receiving case, so in the receiving case, the configuration would be something like this, that your antenna is connected to a load now, and your incident waves are actually falling on the antenna. So a radiation density will be falling upon effective area of this antenna, and that energy will be converted into power, and that power will be delivered to the load. And right now we're considering that this load is directly connected to the antenna. There is no transmission line in between. And the Thevenin equivalent model of this particular configuration is just like this. So the power generated because of the incident waves falling on this effective area, let me model it as a voltage source which is Vt. T stands for the terminal of the antenna. So at this antenna terminal, this is the voltage, this is the voltage source, and this is the input impedance, the antenna impedance ZA, that actually consists of the impedance of the antenna. And now this received power will now be delivered to this load, and let me call this load as ZT. This is the load impedance, or the terminal impedance, I should say. So in this particular case, again we will follow the same you can say same derivation that we have seen earlier for the transmitting case. Here your ZA is Ra plus JXA and ZT is RT plus JXT. So again, for conjugate match condition, RT should be equal to Ra, which is same as R radiation resistance plus loss resistance, and XT should be conjugate of the reactance of the antenna. And in this case, again your IT will be equal to Vt over 2RT, as we have seen earlier for Ig. So the same thing apply over here. Now the current in the whole circuit IT will be Vt over 2RT. And again, because we have a conjugate match, ZA and ZT will be having half of the power at both impedances. So in this case, PT will be equal to 1 over 2 IT square RT. And again, you just substitute IT into this IT over here. You will get the overall PT, which is delivered to the terminal. So this is the power delivered to the load, Vt absolute square over 8 RT, and Vt and IT are the peak values. And then there is a term that is P scattered, because we know that because antennas are they are reciprocal devices. When electric flux density is actually radiation density actually falls on this, some part of that energy is reflected as well. We call this power as scattered power or re-radiated power, and this re-radiated or scattered power is because of the RR, or the radiation resistance of the antenna. So we can find out that value as well. We know what IT is, so P scattered would be half IT absolute square RR. Plug in the value of IT over here, you would see that this comes out to be this. So this is the scattered power or the re-radiated power in case of receiving mode. Again, all these expressions you don't have to memorize, they will be given in your exam, but you should know how these expressions are derived and how they are related with each other. So let's talk about the antenna equivalent area. And this antenna equivalent area, it is actually used to describe the power capturing characteristics of the antenna. It is the same effective area that we talked about earlier in the previous lecture, that the effective area of the antenna actually defines how much power will be received, and we have seen that the effective area AE times the S, which was the radiation density, it will give me the power received by that antenna. So from this same expression we can find the effective area if we know power received by the antenna times the power flux density. or I should say the radiation density in this case. So this is the same thing over here, that the effective area with respect to the spherical coordinate is basically what? It's the power available at the terminal of the receiving antenna. So power received by the antenna P to the incident power flux density from the direction. So the radiation density falling on that particular effective area, the ratio of this will give you the effective area. And again, we can write this effective area as AE, which is equal to PT is the power available at the terminal, and the radiation density here we actually represent it as WI. I is the incident power flux density. So in this case, AE is equal to PT over WI. So as we already know that what PT is, if we go back, we have seen that PT is 1 over 2 IT absolute square RT. So we can plug in the values over here in PT divided by WI will give me the effective area. So in this case, effective area is IT absolute square RT over 2 times 1 over WI. So in this particular case, PT is the power delivered to the load and WI is the power density of the incident wave, and this is the same model that we have seen for the receiving case. So this will give us the effective area of the antenna in the receiving mode. So इसी को हम आगे expand थोड़ा सा करें. AE is, and we can see over here, IT is nothing else. I can get IT in terms of VT as 2 over RT. And in this particular case, we haven't considered the conjugate match case. We are just using the expressions as it is. So you can see this is VT absolute square over 2 WI RT over this is the resistive part, the cumulative resistive part, and this is the cumulative reactance part in this case. So we haven't applied the conjugate match condition right now. So when you apply the conjugate match condition, this whole expression will reduce down to this. So in this particular case, again, RR plus R loss is same as RT, and XA is the conjugate of XT. So this will cancel out and you will have this in terms of RT. And in this particular case, for maximum effective area, if you put RT, which is equal to RA now, will be RR plus R loss. So we can write the maximum effective area will be equal to VT absolute square over 8 WI, which is the power flux density, times 1 over RT, and this RT is also RA, which is also RR plus R loss. Okay, so this AE is the effective area, which is when multiplied by the incident power density is equal to the power delivered to the load, जो भी तक हम बात करते आए हैं. And AS is the scattering area, and this scattering area, how do we actually find this scattering area? Again, if you go back, for P scattering, here you can see P scattering is 1 over 2 times IT absolute square RR. This actually defines the scattered power. So if we come back over here, we can see what effective area is in actual power available at the terminal divided by the power incident power flux density from a direction. So it is PT over WI. So now in this case, we will have this whole power VT absolute square over 8 WI times the resistive part of the antenna RR, which we have seen over here as well, RR. So in this particular case, this will define the scattering area of the antenna. So this much area is contributing to the re-radiation of the antenna as well. So you can actually find out this expression as well, just like we have seen it for the effective area of the antenna as well. So this scattering area, which is when multiplied by the incident power density, is equal to the scattering or re-radiation power. So if you multiply this AS with this the incident power density, you will find the scattered power, which is this P scattered. Okay, so let's quickly have a look at example 2.5. Okay, so example 2.15, let's have a look at this. So in this particular case, a uniform plane wave is incident upon a very short lossless dipole where L is far less than lambda. It is also shown here in the figure 2.29. For the maximum effective area, assuming that the radiation resistance of the dipole RR is 80 pi by lambda, its whole square, and the incident field is linearly polarized along the axis of the dipole. So it shows that the axis of dipole and the linear polarization are in line with each other. So in this case, we have to actually find the overall effective area of the dipole. So for example, for a lossless case, RL will be equal to 0. So in this case, this effective area AEM is now reduced to, you remember last time we have seen the maximum effective area, is represented like this. So for a lossless antenna, this R loss will be equal to 0. So we will have VT absolute square over 8 Wi 1 over RR, which is over here as well. So we need to find this effective area. So the dipole is, since the dipole is very short, the induced current can be assumed to be constant, because the dipole is of very short length, because it is given that L is far less than lambda. So in this case, VT, which is the voltage induced in this case, is just equal to the electric field of the incident wave times the length of the dipole, EL. So VT, the terminal voltage is, in this case, is EL. So here VT is the induced voltage on the dipole, E is the electric field of the incident wave, and L is the length of the dipole. And we know that for a uniform plane wave, the incident power density can be written as Wi is equal to E square over 2 eta. And this eta is basically the intrinsic impedance of the medium. If you remember last time when we talked about representing the gain of the antenna, so I think it was the general expression of directivity, where we saw this expression first here, that the intensity of the antenna can be represented as a function, which is the radiation intensity function, and it is nothing else but the absolute of the electric field square, both theta and phi, divided by 2 eta. So we have used this expression, which is electric field square over 2 eta, to actually find out the electric flux density, which is, in this case, it is intensity U, and we know that U and W are related with each other. You remember it was R square U will give you U. We have seen this before as well. Let me show you this. U is R square W, and W is the power density. So they are directly related with each other. So in this case, let me go back to the example 2.15. So in this case, the the power density can be written as E square over 2 eta, and eta is the intrinsic impedance of the medium, and for free space its value is 120 pi. So you plug in all the values over here. So VT will be EL whole square over, you plug in the value of Wi, which is this, and the value of radiation resistance, it is given. You plug in all the values, it comes out to be 0.119 lambda square. So depend upon the frequency, you can find the effective area of this dipole. Okay, let's talk about the next topic, which is the effective area and directivity. So it is the continuation of the previous topic that we actually discussed in the last lecture. In this case, we're going to talk about the effective areas and the directivities and how they are related with each other. So for example, consider a case where we have two antennas. This is your transmitting antenna, antenna number 1, and this is your antenna number 2 over here, which is the receiving antenna. And both these antennas are at a distance r from each other, and your direction of propagation is from antenna 1 to antenna 2. So this particular antenna, it has the effective area of the transmitting antenna as ATM. This is the maximum area, and DT is the directivity of this antenna, which is the transmitting antenna, and ARM is the maximum receiver effective area, and D is the receiver's directivity. So now in this particular case, if antenna 1 was isotropic, so it means it was not directional, it is an isotropic antenna. So obviously the whole power will be radiated in all directions. So we know that the power density in this case will be the total power PT divided by 4 pi r square. We have already seen this expression before. So in this particular case, this will be power radiated in all direction. But if we have an antenna which has a certain directivity, for example in this case it has a certain directivity, it means it's not isotropic. It means this whole power will be directed in a particular direction. So let me multiply it with this dt. So it will be dt. This will give me the power flux density of the transmitter in a particular direction where the directivity of the antenna is towards. So now in this case, my power flux density of the antenna Wt will be Pt dt over 4 pi r square, which is we have got over here as well. So this is the power flux density which is falling on the receiving antenna. So how much power will be collected by the antenna? So we know that this is the power flux density which is falling on the receiving antenna. If we multiply it by the receiver antenna total effective area, we will get the power received or power collected by that antenna. So we just multiply it by, and this will give me the power received by the antenna, PR. So PR will be Pt dt AR upon 4 pi r square. And this expression is what we have over here. And from this we can find dt AR as, if we just substitute, if we just manipulate with these expressions, from this we can find that dt AR is same as PR 4 pi r square over Pt. We've just manipulated this a little bit and we got this expression which we can see over here, this one. So इसको हम आगे use करेंगे in order to actually come up to a certain point. So अगर for example हम antenna 2 को use करें as a transmitter, so in this case the antenna 2 is being used as a transmitter and antenna 1 is actually used as a receiving antenna. So in this case for example and we are considering that the medium is linear, passive and isotropic, so in this particular case same thing will apply and we will get the expression dr at which will be equal to PR over Pt 4 pi r square, and you can find it yourself. जिस तरह हमने ये भी find किया, you can find this as well. So now if you divide this with the this expression with this expression, we can see that we can come up with an expression dt over at is equal to dr over ar, and here we can see that they are directly proportional to each other. So we can conclude from this that by increasing the directivity of the antenna, the effective area of the antenna would also increase. So if we talk about the maximum directivity, so it will be represented as, for maximum we use d naught t, and for maximum effective area, let me call it ATM, maximum effective area of the transmitter antenna, and this is equal to d naught r over ARM for maximum directivity and maximum effective area. And in case the transmitting antenna is isotropic, then the directivity will be 1. So we can write that ATM or the ATM will be equal to ARM over D naught R, the maximum effective area of the receive antenna divided by the maximum directivity of the receive antenna. This will give us the maximum effective area of the transmitting antenna, and this is the case when the transmitting antenna is an isotropic source. So for example we'll talk about that if antenna number 2 is a short dipole. In this particular case, the antenna 2 is not isotropic source, which we have considered in this case. If it is a short dipole, what will happen now? So let's have a look. Let's quickly have a look. So now in this particular case, let's consider that if antenna 2 is a short dipole and its effective area is 3 lambda square over 8 pi and its directivity is 1.5. It means it is 1.5 times more than an isotropic. So now in this case, my ATM will be ARM over D naught R. So what we're going to do is, in order to find ATM, we're going to plug in the value of the receive antenna. Basically what we have considered is that this is your transmitting antenna and this is now your receive antenna. So this receive antenna is your small dipole, and this antenna is a isotropic source. So this is the case that we're discussing right now. So in this particular case, the ATM will be equal to, it means the effective area of the transmitting antenna will be equal to, plug in the value of ARM and D naught R over here, it comes out to be lambda square over 4 pi. And from that we can see that if we want to find the effective area of the receiving antenna, this is the transmitting antenna and this is the receiving antenna. For receiving antenna, we can find it from this expression directly. So basically this ATM is ARM over D naught R. So ARM will be D naught R ATM, right? So for isotropic case, when our transmitter was TX was isotropic, and this is a very important point, if transmission antenna was isotropic, the effective area of the transmitter comes out to be lambda square over 4 pi. And our receive antenna, is a short dipole, the effective area Rx is short dipole, the ARM or the maximum effective area of the receive antenna is D naught R times ATM, and ATM is what? It is lambda square over 4 pi. So what we can conclude from this particular expression is that the maximum effective area of any antenna is related to its maximum directivity by this expression. So it means whenever you want to find the effective area of any antenna, you just multiply the directivity of that antenna with lambda square over 4 pi. That's all what it says. And for isotropic, because we know the directivity is 1, so we have 1 over here. So the same expression applies for an isotropic antenna as well. For in this particular case, ARM is D naught R times lambda square over 4 pi. And this is the case when we are considering that there is no conduction, dielectric losses, there is no polarization mismatch and extra. So if we include all those expressions over here, so the effective area is now lambda square over 4 pi D naught, which is this, and then ECD represents the conduction and dielectric losses. 1 minus gamma absolute square is the reflection efficiency, and these polarization unit vectors, we remember this is the polarization loss factor, PLF. So this shows like the polarization mismatch. So if you incorporate these efficiencies in this expression, it will give you the overall general expression of the of finding out the effective area of an antenna. Okay, let's talk about Friis transmission equation. So this transmission equation actually relates power received to the power received to the power transmitted between two antennas. So PT and PR, the power transmitted and power received by an antenna, it actually relates these two entities with each other. So if we just discuss this transmission equation, so the case is that you have antenna over here and you have a receiving antenna over here. So this is your TX antenna and this is your RX antenna. So this Friis transmission equation actually relates that the power transmitted from the transmit antenna and the power received by this antenna, how these two are related with each other, how PT relates with PR, so that we can actually determine that if this much power is being transmitted and considering all the factors that are involved, we can determine how much power will be received by the antenna. So this is what the Friis transmission equation actually tells you. So in this particular case, the Friis transmission equation relates power received to the power transmitted between two antennas separated by a distance r greater than 2d by lambda square. And if you remember this expression, this r greater than 2d square by lambda, it is nothing else but considering that the distance between the two antennas is greater than the case where we consider that in order to be in the far field, the radiation should be considered at a distance r, which is 2d square by lambda. So if you go back to the radiation zones where we actually saw the far field and near field expressions, when r is greater than 2d by lambda, it is considered to be in far field. So this is what we are considering here, that both the antennas are at a distance r from each other. It means they are at least separated by a distance where the transmission from the transmit antenna will be considered as in far field when it will be received by the receive antenna. So the power density at a distance r from the transmitting antenna, we can actually find this power density as well. So for example, if you have a transmitting antenna, and you can see there's a pointing mismatch. So we can see that this antenna is radiating in a spherical direction, theta r and phi r, and this receive antenna is pointing in a direction transmitting antenna is theta t phi t, and the receiving antenna is directed towards theta t and phi the transmit antenna is directing towards the angle theta t and phi t, and the receiving antenna is pointing towards the spherical direction of theta r and phi r. So obviously there is a pointing mismatch, so we have to consider that into our equation as well. So in this particular case, this transmit antenna is transmitting with the power pt. Its gain is gt, directivity is dt, the conduction and dielectric efficiency is represented as E, gamma I or gamma t in this case is the transmitting reflection coefficient gamma, and this is the polarization unit vector in case of transmitting. So it is represented as rho t with a cap on top, and the receiving antenna is represented by all these parameters as well, and both these antennas are separated by a distance r. So if you want to find out what is the power flux density transmitted by this particular transmitting antenna, so we can find that Wt just like we have seen before, that power flux density is same as the power transmitted by the transmitter over 4 pi r square. So if this is a directive antenna, we can with a specific gain g, we can find that we can multiply it by t as well. So it is the power flux density will be pt gt over 4 pi r square, and we know that gt is nothing else but the efficiency of the transmitting antenna times directivity dt. So we can write this as pt and dt theta phi, and just multiply by the efficiency et over 4 pi r square. Okay, so in this particular case, this is the expression we are talking about over here. So this expression actually represents the overall power flux density Wt. So the effective area of the receive antenna, what is going to be the effective area of this? We have already seen that the effective area of any antenna is equal to the directivity of that antenna, say d naught, times lambda square over 4 pi, which we have seen in the previous slide as well over here. That effective area of antenna is d naught times lambda square over 4 pi. So we are going to use this expression to find the overall effective area of the receiving antenna, to find out how much power is actually received by this antenna. So the effective area of the antenna AR is directivity times lambda square over 4 pi. This directivity is the directivity of the receiving antenna, and ER represents the efficiency of that antenna. So it is ER times DR times lambda square over 4 pi. So when this power flux density Wt will fall upon AR, you will get the power received by the receiving antenna. So power received will be, just multiply this expression with this, you will get PR is equal to ER dr lambda square over 4 pi Wt. In this case we can see dr, now these coordinates theta and phi are r coordinates, or the coordinates of the receiving antenna where it is pointing towards, and you plug in the value of Wt over here. This is what Wt, and you plug in the values. This is going to be our overall expression of the receive power, which is, let me just write it down. So this is PR is the efficiency of the transmit antenna, efficiency of the receive antenna, then you have directivity of the transmitting antenna in the direction theta t and phi t, and the directivity of the receiving antenna in the direction theta r phi r, and then whole divided by, because we have 4 pi r square and this is 4 pi, when they will multiply together, it will be 4 pi whole square. And then because we have a pointing mismatch, or if there is a polarization you can say mismatch, then we will have the polarization pointing vectors, this rho t dot product with rho r absolute square. So this is nothing else but polarization loss factor. So this expression determines how PR and PR is related with PT. So I forgot to write PT over here. So here we have PT as well, because here we have PT. So in this particular case, we can see how PT and PR are related with each other. So from this whole expression, we can actually determine the relationship of PR and PT. We can see that PR over PT will be equal to ET, ER, DT, let me just skip these coordinates, dr over 4 pi r square, and then this times polarization loss factor. And one thing we have also missed over here in the previous one is this lambda square. So we have lambda square here as well. So that lambda square will come out to be here. And in this whole particular thing, we know that dt et is nothing else but the gain of the antenna, and dr into efficiency is the gain of the receiving antenna. So we can write this whole expression as PR over PT. It is GT GR lambda square over 4 pi r square times PLF. So if, for example, and basically this expression is what is written over here, and if we include the conduction and dielectric losses of the transmitter and the receiver, and the power power reflection coefficient at the transmitter and receiver as well, if we incorporate all these things into it, this is the whole expression that defines the relationship between the received power and the transmitted power. So if, for example, the reflection and polarization matches antenna, for reflection and polarization matched antennas aligned for maximum directional radiation. So in this case, ECD and ECDR, these two will be 1. Gamma will be 0, so these two terms will be 1 as well. And we have no polarization mismatch, so polarization loss factor will also be 1. So we will be left with only this part. And in this particular case, because there are no the efficiency is 100%, then we can say directivity is directly related with the gain of the antenna. So in that case, if the angles are pointing in the same direction as well, then we can say this is the maximum gain of the transmitter and maximum gain of the receiver. So in this particular case, polarization loss factor will be equal to 1, and this whole thing we can write as PR over PT. This is equal to GT, G naught I should say for the maximum gain, and G naught R over 4 pi R by lambda whole square. We can write it like this. So in this particular case, this expression is called free space loss, and we can see this free space loss actually depends upon the distance R between the transmitter and receiver. So this expression is known as the Friis transmission equation that actually relates the received power with the transmitted power. Okay, so let's now talk about the last part, which is the radar range equation. This radar range equation is similar to that of Friis transmission equation. The only thing is that the scenario is slightly different. In this particular case, we have a transmitting antenna, and this is how a radar normally works. So the example we're looking at right now is an example of a bistatic radar, in which you have a separate antenna for transmission and you have a separate antenna for reception. Normally you can use the normal radars. They actually transmit and receive at the same time by having a certain pulse repetition frequency. So it is transmitting at one time, and then it is actually listening for the echoes. But in this particular case, we're considering a bistatic radar where an antenna with all these parameters, PT, GT, DT, the efficiencies, reflection coefficient, and the polarization pointing vector, and then you have a receiving antenna with all these parameters as well. So in this case, this particular antenna is transmitting the electromagnetic waves in a particular direction, and considering at a distance R1 there is a target, and that target has a specific cross section, and what that cross section is, we'll talk about it later. So this target actually comes in the way of this incident wave, and what happens is when this electromagnetic waves fall upon this target, that electromagnetic waves induced currents on the surface of the target. And whenever there is induced current, you would say that the antenna itself will start radiating. So this antenna will be radiating in all directions. So it will be and that part of power that that part of incident wave that is that induced a certain current on the surface of this target will radiate electromagnetic energy in all directions, and some part of that energy will be reflected towards your biostatic radar receiver at a distance r2. So when that energy is received by this receiving antenna, you would know that there is a target present at a distance r2 from its location. So how do we define this radar cross section? By definition, the area intercepting the amount of power which, when scattered isotropically, produces at the receiver a density which is equal to that scattered by the actual target, known as the radar cross section or echo of the target. In simple words, it just says that this is the effective area of the target that is actually transmitting energy in this particular direction. Although it is transmitting in all directions, but we are interested in the power that is being reflected in the direction of the receiving antenna. So this radar cross section is the effective area of this target that will be generating that much electromagnetic flux that will be directed towards the receiving antenna. So that effective area is called the radar cross section, or it is also known as echo area, and the symbol is sigma in this case. So mathematically, how do we actually define this? Again, we can find out the incident electric. We can relate incident the electromagnetic density or the magnetic or the electric flux density and the scattered you can say flux density or power density in this case. How they are related with each other? Let me just write it down. Radar range equation. For this case, this is our transmitting antenna and there is a target here in space. So this is a distance r1, and at a distance r2 we have our receiving antenna. So this is the radar cross section of the antenna here. So the power flux density which is falling on the target, let me call it the WT, or the power flux density incident on the target. And this power flux density, when it will fall on the target, it will induce currents, and it will again rescatter the energy in different directions, and some part of that radiation will be scattered towards the our receive antenna which is at a distance r2. So we can relate this scattered power density with the incident power density as this omega s will be equal to the radar cross section sigma times the power received power received by this target. And how do we actually find this out? We know that the power received by this would be the area of this particular target times the incident power density. So power density times the radar cross section, this will be the power now available at the transmitter. And now this is now the power induced by the electromagnetic this omega I, which is the power density incident on the target. Now it will radiate that energy equally in all direction. So this whole power will be distributed over 4 pi r square, just like an isotropic source. So in this particular case, your power flux density will be equal to sigma times Wi over 4 pi r square. And since we say that the target is very far from the antenna, we can say that it is when you apply a limit when r is approaching to infinity. R is very far. So in this case, your Ws, or the scattered power density, is related with the incident power density as limit r approaches to infinity cross section times the incident power density over 4 pi r square. This is what we have given over here. So from this expression, this mathematical expression, we can actually determine the the value of radar cross section. So we're just manipulating this expression. So this sigma, which is the radar cross section, is limit r approaches to infinity 4 pi r square ws over wi, the scattered power density to the incident power density. And we know that the power densities are related with the electric field, you can say the incident electric fields and the scattered electric fields. We have already seen that expression, if you remember, that your u is 1 over 2 eta e square. We've already seen this as well. So for incident, this would be this, and for scattered, it would be es. So that's all what we have done over here. So we have replaced ws with es absolute square, and wi with ei, or the incident electric field absolute square. And because we know that they're same as considering the magnetic fields as well, so both are equal as well. So in this particular case, the sigma is the radar cross section or the echo area in meter square, r is the observation distance from the target, wi is the incident power density, ws is the scattered power density, ei and hi are the incident electric field or incident magnetic field. So you can consider any one of these two. So now let's see that by using the definition of the radar cross section, we can consider that the transmitted power incident upon the target is initially captured and then it is re-radiated isotropically. This is what we have discussed so far, that the power density which has fallen on the target, it actually induced certain currents on the surface of the antenna, and that induced current will again generate electromagnetic waves and they will radiate in all directions isotropically. So the amount of power captured by the target, let's call it PC, is obtained by multiplying the incident power density by the radar cross section. This is what we have done over here, the incident power density into radar cross section sigma. So this PC is sigma times Wt, and you just replace Wt over here, it is sigma times Pt Gt over 4 pi R1 square. So R1 is the distance from the transmitting antenna to the target. So in this particular case, PC, which is the power captured by the target, is equal to the effective area of the target, which is the radar cross section, times the Wt, or the power flux density or power density falling on the target. And we know how to find this Wt. How do we find this Wt or Wi in this case? In this particular case, this is nothing else but power transmitted by the antenna over 4 pi r square, and if there is a gain to that antenna, we just write Gt over here. So that is what is written over here. So sigma Pt Gt over 4 pi r square, and since r is r1, so we have replaced it over here, and we know that Gt is ET, or the efficiency of the transmitting antenna, times the directivity of the antenna. We just replace that value over here. So the power captured by the target is now radiated isotropically, and the scattered power density can be written as Ws will be this captured power is now radiated isotropically, and it is isotropically radiated in all direction. Here you can see it is not scattered in all direction. So at a distance r2, this whole scattering will be received by this particular antenna at a distance r2. So in this case, we can say that Ws will be equal to the power captured by the antenna divided by 4 pi r2 square, because it is radiated isotropically in all direction. So you plug in the values of PC, which we have already seen over here. You plug in the value over here. This Ws will be equal to ECD T, this is the efficiency of the transmitting antenna, Pt dt over 4 pi r1 r2 whole square, because you have 4 pi r2 square and you have 4 pi r square. So you plug in the values over here, you can see it comes out to be 4 pi r1 r2 whole square. Okay, so now this is the power that is radiated by the target now, and this omega s, or the scattered power density, is now received by the receiving antenna. So what is the power received by this antenna now? This power will be equal to the effective area of this antenna times the scattered power Ws. So this is what is done over here, that the received power is the effective area of the receive antenna times the scattered power density. And we know that what AR is. AR is lambda over, let me just write it down. We know that AR will be equal to directivity of the receiving antenna times lambda square over 4 pi. We've already seen this earlier. So in this particular case, we know what WS is EC dt times PT dt into lambda over 4 pi R1 R2. And what AR is the efficiency of the receiving antenna times dr divided by multiplied by lambda over 4 pi, which is this. So when we say power received will be equal to AR times WS, and AR is the efficiency of the receiving antenna times dr lambda square over 4 pi, we know what WS is. WS is this E, efficiency of the transmit antenna, PT dt, and then over 4 pi R1 R2 whole square, this one, right? So if we just simplify this, power received is ER ET, and then we also have a cross section over here, sigma. So this will be equal to sigma dt, this one, dr, this one, and then divided by 4 pi, this is 4 pi, and then we have lambda square here, so into lambda square over 4 pi R1 R2 whole square. So this whole expression, you have got this by evaluating this PR, which is AR WS. So now in this case we have PR is equal to AR times WS, which is ET times ER, radar cross section PT dt dr over 4 pi times lambda over 4 pi R1 R2 whole square. And if you want to find the ratio of PR to PT, so PR over PT will be this whole expression. So this will relate the power transmitted by the antenna and the power received by the receive antenna is now related by these this expression. So since we have not considered the reflection losses and polarization losses, P over PT would be, if you incorporate the reflection coefficient at the transmitter and the reflection coefficient at the receiver and the polarization unit vector or the polarization loss factor into account, this whole expression will represent the relationship between the received power and the transmitted power. This expression is the general expression of radar range equation. So for polarization matched antenna, like in this case, we're considering that there is no polarization loss factor, the efficiency is 100%, and there are no reflection coefficients. In this case, this whole expression will reduce down to this expression, which is PR over PT, radar cross section times gain of the transmit antenna, gain of the receive antenna over 4 pi into lambda over 4 pi R1 R2. So in this particular case, this is the gain of the transmitting antenna, gain of the receiving antenna. R1 is the distance from the transmitting antenna to the target, and R2 is the distance from the target to the receive antenna. And we know that this sigma is the radar cross section. So this whole expression actually determines the relationship between PR and PT. So it relates power PR delivered to the received load to the input power PT transmitted by an antenna after it has been scattered by a target with a radar cross section or echo area of sigma. So this is what is called radar range equation. So this actually concludes our chapter number 2. So we have covered all the topics related to the parameters of antenna. So if I go back to the course outline for this particular chapter, we have covered all these topics. So what I expect from you guys is that you will go through the end chapter problems and you will try to understand how you can apply all these relationships to actually solve the end chapter problems. So if you have any question, you can text me, or you can send me a message on WhatsApp, or you can even email me, and I will get back to you as soon as possible. Next time we will talk about chapter number 3. and we'll talk about those contents in detail in the next lecture. So that'll be all from my side. Thank you very much.